We've looked at the quality of a regression model from the viewpoint of the root mean squared error or RMS error. But when it comes to linear regression, there are other measures that also allow us to evaluate the quality of the model. Okay, so let's look at an important way of quantifying the quality with which a linear regression model fits the data. So let's say that you've got a bunch of homes, continuing from the previous example, and the average household value is 250,000. Okay, so that is, you've got data on a number of homes, and the target attribute is the value of the home. And let's say the average value of the target attribute is 250,000. Okay, now suppose you're not given any other information, and you're told, I've picked a home from this data set whose average value of the house is 250,000. What is your best guess for the price or the value of the home that I have picked? Okay, clearly, in the absence of any other information, your best prediction for the value of a random household is going to be 250,000. Right? That's the best you can do because you're told that that's the average. And your best prediction over the long run, that is, if you are asked to make this prediction many, many times, and over the long run, if you see how close you come to the actual value, right? Over the long run, guessing the mean value is the best thing that you can do, right? So without any additional information, you guess the mean. And that is kind of the naive approach in regression, right? Remember, in classification, the naive approach was to go with the majority. In regression, the naive approach is to go with the mean. Okay, so let's take just a single point for convenience. Of course, we've got data on many houses with rooms as the predictor attribute, price of the home or value of the home as the target attribute. And here's one point, which the number of rooms is 5 and the price is 250,000. Okay, now forget for the time being that I said the average is 250,000. For this particular example, we are using a different average. Okay, the average is different. 250,000 is not the average here. Okay, let's say the average is 350,000. Okay, so this is the average. This would be our prediction for any house. But here is a home in whose value is only 250,000. It has 5 rooms. Okay, so in the absence of any information for this particular house, our prediction would be its price is 350,000. Okay, so our error would be this: 250,000 minus 350,000. The error is about 100,000. Forgetting for the moment the order in which you do the subtraction, let's say it's mean minus the actual value. The error is 100,000. Okay, so if you use the naive approach and simply predicted the average, for this particular point, your error would be 100,000. Okay, but now I'm showing you only one point. There are many points, right? So using the linear regression model, suppose we've created this regression line, which is the least squares line, as we discussed earlier. Okay, let's say the regression line turns out to be like this. Now your error is this, right? Because your prediction would not be the average this time. Your prediction will be using the regression model, and therefore you will predict this, which is that. Let's say that is 325,000. Okay, so with the model, your prediction for this home turns out to be 325,000. Without the model, it would have been 350,000. Okay, so your error now is 75,000. Okay, so you reduce the error by 25,000. That's what the model helped you to do. Without the model, your error would have been 100,000. With the model, your error now is 75,000. Okay, so we reduced the error by 25,000. That's what the model did. Okay, so let's take a generic example. So suppose you have a point here which is xi, yi, which is, the xi standing for the rooms and yi standing for its price, right? And y bar is the average value of price. Without the model, your prediction would be y bar, and your error would be this, yi minus y bar. That would be your error. In this case, it would be negative because your value is less. Okay, it depends on which order you do it. Okay, so yi minus y bar is negative. Now for the same scenario, suppose you do the linear regression line. Of course, I've extended the line to meet the y-axis, the intercept. Your prediction is now going to be y hat, which is the model prediction. Remember, we are using the hat to indicate a predicted value. It should be yi hat. Okay, so therefore, using the regression, we can reduce the error from yi minus y bar being the mean, to yi minus y hat. Yi hat should be, right? Because yi hat is the prediction for y. Okay, thereby we decrease the error by yi minus yi hat minus y bar. Okay, that's what this is. This is yi hat minus y bar. We reduce the error from this to this. Okay, so that's what the regression model is doing. It's allowing you to reduce the prediction error, right? Now, sometimes people use the term, the expression that regression is explaining some of the variation. Okay, let's discuss what that means. What we are saying is, you're seeing a bunch of homes whose average price, let's say, is 350,000, but there's a variation. Some homes cost more, some homes cost less, or some homes are worth more, some homes are worth less. Okay, so there is variability in the price of homes. There is variability. Okay, now in the absence of any other information, you may wonder, well, what's happening? Why are these prices different? In the absence of any other information, we think there is this variability. Okay, now the regression comes along and tells us, look, homes with lower number of rooms have lower price. Homes with higher number of rooms have a higher price. Okay, and therefore this home seems to have a value less than the average. Why? Because it's got a lower number of rooms. Probably the number of rooms is less than average, so its price is going to be less than average. Okay, how about this home? Why is this, suppose there were a point here, why is this home worth so much? Well, it's got a lot more rooms. Okay, so what we are saying here is we are now able to explain to some extent why price is varying. Why? Because in this example, with simple linear regression, we are saying, look, the price is not just happening at random. The price is being determined at least partially by the number of rooms a home has. That's an explanation for why home prices vary. Okay, so sometimes people talk about regression as explaining the variability in the target attribute. So now we can talk about this. We can say that portion of the total deviation or total variation in the home prices explained by the regression is that much, y hat minus y bar. Okay, this much difference is explained by the regression, right? It's telling you that this house has a lower number of rooms, and therefore its price is also below the average by so much. Okay, so that is the part which is explained by the regression. But this remaining part is unexplained by the regression. Okay, I understand that this house is going to have a lower price because it's got lower number of rooms, but why is it so low, right? The regression says it should be this, but in reality it is so much. So we say this part of the variation is unexplained. Okay, that is why they call it the residual, right? It is the residue of what is left over after the regression has explained some of the variation. This is the residual which is not yet explained. Okay, so that is why they call this the residual. Now we come to an important aspect about linear regression. Okay, so first of all, again, I spoke about regression or linear regression as explaining the variability in your target attribute. Okay, so let's look at what is the total variability in the target attribute. Okay, that is what is called as the total sum of squares, TSS, right? How do you calculate that? Say yi minus y bar the whole square. Okay, that is y bar is the average value of the target attribute. So for example, if this was the price, then y bar would be the average price. So for every data point, we are taking its difference from the mean and we are squaring it. Okay, that reflects the amount of variability that exists in the prices, right? So for example, if all the homes had exactly the same price, right, then there is no variability at all because they all have the same price. There are 100 homes, every single home has a price of 350,000. There is no variability, and if you calculated what is the equation that is shown on the slide, you'll get a value of 0 because there is no variability. Everything is exactly the same, right? But let's say you've got one house, some houses which are less, some houses which are more. Now there is variability, right? So in order to quantify the total amount of variability that exists in the home prices, one very convenient way to do that in statistics, and we'll be returning to this quite often, one very convenient way to do that is to first calculate the mean, take a look at how much each value varies from the mean, square it up, and add up all of those squares. Okay, the sum of squared deviations. We looked at this when we talked about RMS error. This is exactly the same thing, the sum of squared deviations. But in RMS error, we were talking of sum of squared deviations from the prediction. Here we are talking of sum of squared deviations from the mean. Okay, as a measure of how much variability there exists in a set of values. Okay, this is what is called as the total sum of squares, or TSS. Okay, so this is all the variability that exists in your target attribute. Okay, the next thing we're going to talk about is how much of this variability is accounted for by the predictor attribute X. Okay, so for example, when you talk about Y, think of price of the homes. When you talk about X, think of rooms, right? So how much of the variability in the home prices is accounted for by the variation in the number of rooms? That is what is called sum of squared regression. And that is calculated as yi hat minus y bar the whole square. Okay, so that is how much is the difference between the predicted value and the mean, right? Because this is where the improvement in your prediction comes along. Without the regression, we would have said mean. With the regression, we are saying yi hat. So that is the difference, which is the improvement brought about by the regression. And this is called sum of squared regression. Okay, and unaccounted variability is sum of squared errors, which is yi minus y hat the whole square. Sum of squared errors, right? Because this is the actual value. This is what the regression predicted. And this is what we'll be using, of course, to calculate the RMS error. Okay, let's just jump back to our previous slide a little bit. Okay, so if you look at the difference between the point and the mean, that is sort of like the total sum of squares. Of course, here these are not squared, but think of the distance from the mean line to the point as the total variation to be explained. So now this much is the variation that is explained by the regression. This much is the variation that is not explained by the regression. So this is your sum of squared regression. Okay, and this is the residual sum of squares. Okay, the sum of squared errors. Okay, so you can see here, this is the total amount of variability that needs to be explained. This is the amount of variability that the regression actually explains. This is the part that the regression is unable to explain. That is what is a residual. Okay, and it's a property that TSS is always equals SSR plus SSE, sum of squared errors. Okay, this property always holds, and therefore if you find that this is the amount of variation that the regression explains, this is the total amount of variation to be explained. So this ratio tells you what proportion of the total variability is explained by the regression. Okay, in other words, the the regression is able to explain, let's say, 70% of the total variability in prices. Right? That's also a measure of how good your regression model is. Okay, and this value, when calculated for this value, is called as the R square. Okay, it's called the coefficient of determination, and basically it tells you what proportion of variability is explained by the regression. The regression is able to account for so much of variability. Okay, this is the square of the correlation coefficient in the case of simple linear regression. So the sum of squared errors is this, right? Because error is nothing but the actual value minus the predicted value squared, right? This is the error for each case. You square it, you get the squared error. So that's your sum of squared errors. And therefore, you can talk about the squared errors per case or per row, which is nothing but sum of squared errors divided by n, right? There are n rows accounting for so much of squared errors. So per row, you have SSE divided by n, and a root mean squared error is nothing but square root of this sum of squared errors divided by n. Okay, it's the same thing that we discussed earlier. Okay, so till now we've talked about simple linear regression. Multiple linear regression is just that you've got many attributes. Okay, beta 1, beta 2, beta 3, beta k. So you've got many predictor attributes, not just one predictor attribute as in the previous case. Okay, so multiple independent attributes, in other words, multiple predictor attributes, one dependent attributes, in other words, one target attribute. Okay, with multiple linear regression, what you're fitting is not a straight line, right? Because it's happening in more than 2 dimensions, right? So you're talking about in 3 dimensions, it would be a plane that looks like this. In more dimensions, it's called as a hyperplane.